Now let's look at different mechanical forms of work. There are several different ways of doing work, each in some way related to a force acting through a distance. In elementary mechanics, the work done by a constant force capital F on a body displays a distance of simple s in the direction of the force is given by W is equal to Fs in kilojoules. If the force F is not constant, the work done is obtained by integrating the differential amount of works, which is going to be equal to, or W is going to be equal to integral of F ds between points 1 and 2. Obviously, one needs to know how the force varies with displacement to perform this integration. Equations which we learned above give only the magnitude of the work. The sign is easily determined from physical considerations. The work done on a system by an external force acting in the direction of motion is negative, and the work done by a system against an external force acting in the opposite direction to motion is positive. There are two requirements for a work interaction between a system and its surroundings to exist. Number one, there must be a force acting on the boundary, and number two, the boundary must move. Therefore, the presence of forces on the boundary without any displacement of the boundary does not constitute a work interaction. Likewise, the displacement of the boundary without any force or opposite or drive this motions, such as the expansion of a gas into an evacuated space, is not considered an interaction work or a work interaction, since no energy is transferred. In many thermodynamic problems, mechanical work is the only form of work involved. It is associated with the movement of the boundary of a system or with the movement of the entire system as a whole. Some common forms of mechanical work are discussed in the next slides. Now let's look at shaft work. Energy transmission with a rotating shaft is very common in engineering practice. Often the torque capital T applied to the shaft is constant, which means that the force capital F applied is also constant. For a specified constant torque, the work done during simple n revolutions is determined as follows. A force capital F acting through a moment arm simple r generates a torque capital T of capital F simple r. In this case, the force is going to be equal to capital T torque divided by simple r. This force acts through a distance s, simple s, which is related to the radius r by s would be equal to 2 pi r times simple n. In this case, recall that n would be the number of revolutions, and anywhere where you see a dot on top would suggest the rate. So shaft work in this case is determined from capital W sub sh, that is shaft work, would be equal to Fs would also be equal to the torque divided by the radius times 2 pi Rn, which would also equate to 2 pi Nt, where N is the number of revolutions and T is the torque. The power transmitted through the shaft is the shaft work done per unit time, which can be expressed as W dot sub shaft sh would be equal to 2 pi n dot t, where n dot is going to be the number of revolutions per unit time. Now let's look at spring work. It is common knowledge that when a force is applied on a spring, the length of a spring changes. When the length of the spring changes by a differential amount of dx under the influence of a force capital F, the work done is denoted by delta W of spring would be equal to capital F dx. To determine the total spring work, we need to know a functional relationship between capital F and x. For linear elastic springs, the displacement x is proportional to the force applied, that is, capital F is going to be equal to kx, where k is the spring constant and has the unit of kilonewtons per meter. The displacement x is measured from the undisturbed position of the spring, that is, when x is equal to 0, when f is equal to 0. Substituting this above equation and integrating would yield W spring would be equal to 1/2 k times x2 squared minus x1 squared, and the answer would be given in kilojoules. And in this case, x1 and x2 would be the initial and the final displacements. Now let's look at work associated with stretching of a liquid film. Consider a liquid film such as soap film suspended on a wire frame as given in figure 2.35. We know from experience that it will take some force to stretch this film by a movable portion of the wireframe. This force is used to overcome the microscopic forces between molecules at the liquid-air interfaces. These microscopic forces are perpendicular to any line in the surface, and the force generated by these forces per unit length is called the surface tension, sigma. The units of sigma is going to be newtons per meter. Therefore, the work associated with the stretching of a film is also called surface tension work and is determined from sigma s dA integration between points 1 and 2, where dA would be equal to 2b dx and is the change of surface area of the film. The factor 2 is due to the fact that the film has two surfaces in contact with air. The force acting on the movable wire as a result of surface tension effects is 2b sigma s, where sigma s is the surface tension force per unit length. Let's now look at work done to raise or to accelerate a body. When a body is raised in a gravitational field, its potential energy increases. Likewise, when a body is accelerated, its kinetic energy increases. The conservation of energy principle requires that an equivalent amount of energy must be transferred to the body being raised or accelerated. Remember that energy can be transferred to a given mass by heat or work, and the energy transferred to this case obviously is not heat since it's not driven by a temperature difference. Therefore, it must be work. Then we conclude that 1. The work transfer needed to raise a body is equal to the change in the potential energy of the body, and 2. The work transfer needed to accelerate a body is equal to the change in the kinetic energy of the body. Similarly, the potential or kinetic energy of a body represents the work that can be obtained from the body as it is lowered to the reference level or decelerated to zero velocity. Now, from the information that you have gathered thus far, try to solve this problem. Pause the slide and try to solve it by yourself. And if you get stuck, advance it once, and with the information that is given as help, try to solve it again. And if you still get stuck, advance it once more and use the information that is given as help and try to solve it by yourself. And in this case, the power required to accelerate a car to a specified velocity is to be determined. And for this, you are going to be using the energy balance equation that you learned thus far. And in this case, you will notice that the energy, the mechanical energy that is required is a function of the flow energy, the kinetic energy, and the potential energy differences. And you will notice that in this case, there is no flow energy that is associated, so that term becomes 0. And there is no potential energy difference, and that term also becomes 0. And as a result, the change in mechanical energy would be a sole function of the difference of kinetic energy, which is of course a function of the final velocity and the initial velocity. and with this information try to solve the problem.